Now, it turns out that it's not just the electron nucleus system that has quantized energy levels, and it's not just vibration. What else could a diatomic molecule do besides vibrate? It could rotate. And it turns out that the rotational energy also has discrete, separate energy levels. And what it really, so rotational energy levels, the spacing of rotational energy levels for a diatomic molecule usually ends up looking something kind of like this, where the spacings get bigger and bigger. Now, there's no potential energy associated with rotation, so we're just talking values of kinetic energy here. And where this really ends up coming from is because the angular momentum the molecule can have only certain values. So we're going to put off really talking about what how the equation for how you'd calculate these levels until we actually talk about angular momentum, and then we can come back and calculate the energies that things could have as a result. But just about every kind of energy you can think of for a microscopic system turns out to have this property that only certain discrete separated values of the energy are possible. And the amount of energy between one energy level and another changes. So we've already seen that, so for vibrational energy levels, it's something like a hundredth of an electron volt, 0.05 electron volts we saw. For electronic energy levels, like the atoms we started out talking about, like hydrogen, we're talking about energy separations of 1 to 10 electron volts, and these are ranges, okay? Now, it turns out that a nucleus itself can have different values of kinetic plus potential energy because inside the nucleus, all the protons and neutrons are all moving around. So they can have kinetic energy and potential energy too. So inside the nucleus, these energy levels are separated by kind of large numbers, 10 to the 6th eV. And even a single particle that's made of quarks, a hadron, like a neutron or a proton or some excited states of these things, can have energy levels that correspond to different states of the quarks moving around differently, and those are very high. And just for completeness, we'll stick in rotational energies, something like 10 to the -4 eV. This, by the way, is how your microwave oven works. It provides photons of an energy that is very close to the transition from one rotational energy level to another for water. So it makes the water molecules in your food rotate faster, and it gets hot. Yeah. So that's the basic scheme. And it's interesting. So it's really just the basic. So what's the take-home message? The take-home message is the energy principle works for microscopic systems as well as macroscopic systems, and that for these microscopic systems, we find that for any kind of energy we look at, only certain discrete or quantized values of that energy seem to be permitted, and others don't seem to happen. And that if we think about photons as little particles that deliver packets of energy, then if we look at the way the photons interact with the system, we look at the emission from excited gases, or we look at absorption, it allows us to figure out what the energy structure of this thing is, just like we did that problem on the board. So that's the That's the bottom line. Questions about this? I suggest that you read the chapter because it sort of helps get the conceptual framework. There's also at the end of the chapter a little case study that actually talks about lasers and some ideas about how lasers work based on this, so that's sort of interesting.